Hello everyone, welcome back to alkaline hydroxide 784, and today the topic that we are covering is the Maclaurin series. And well, if you do not know what I'm talking about to begin with, then either you haven't learned it or well, you're not in a good state, I suppose. So, you should at least know this one thing. Even if you do not know everything, you must know this one thing at the very least. It is pretty, I think this is like one of the easier things to know, so yeah. Okay, so I have the MF26 open in my computer, but yeah, because there might be something that I do not remember properly, like, the approximation stuff. Yeah. So I have that for reference purposes. Okay, so and why did I tell that though? That was pretty useless for this. Okay, never mind. Let's start. Okay, so well, so what do you use the Maclaurin series for? First of all, basically, if you had something like what one x plus 5 whole thing squared, it's very easy to expand it, right? But what if your x plus 5 was to the power of 100? How would you expand it? Your mind would just explode if you were to try to do them individually, like literally write it 100 times and then multiply them manually. That would be terrible. So that's not a good idea. Don't do that. So instead of doing that, you use the standard series expansion. Of course, this doesn't. I mean, this is not necessarily the most related thing to Maclaurin series, but it's also a series. So it's also some kind of a series expansion kind of thing. So first, let's cover that. Okay, so for this, if you use 1 plus x to the power of n, like for any other term, a plus b to the power of n, how do you expand it? The first thing you should do is to realize that when you're doing lower powers, so if it's to the power of 1, of course it's just a plus b. If it's to the power of 2, it would be a square plus 2ab plus b square, and then to the power of 3 you will get a cube plus 3ab square, sorry, a square b plus 3ab square plus b squared. And for the power of 4 you will get a to the power of 4 plus 4 a to the power of 3b plus 6 a to the power of 2b squared plus 4 a to the power of 8b cubed plus b cubed. I do not remember. Plus b to the power of 4, yeah. See, even for like the power of 4, your mind starts to slow down. Unless you're writing it down, I guess. Maybe that'll be faster. But yeah, when trying to tell it out, it's already hard. But okay. But what's the pattern here? Like, we saw 1, and then you have 1, 2, 1, and then you have 1, 3, 3, 1, and then you have 1, 4, 6, 4, 1. Let me tell you this. This is actually a part of a triangle. Well, I forgot the name of the triangle. What is it called? Is it Pascal's triangle? I think so. Anyway, so there's a triangle that you can create where you start with 1 and you bring it down both sides. And for each number below, you just need to add the two numbers above it, and you get the number. So if you start with 1, and you have 1, 1, then you have 1, 2, 1, you have 1, 3, 3, 1, 1, 4, 6, 4, 1, you have 1, 5, 10, 15, wait, no, not 15. Never mind, 1, 5, 10, 10, 5, 1. And then you have 1, 6, 15, 20, 15, 6, 1. And you get the idea. And I'm telling this even without writing it because I record this separately from writing it down. So yeah, cool. But you don't. So this is like the easy way of thinking about it. But if you had to do this for 100, you're not gonna write a triangle for 100 terms, are you? Instead, you use the formula that they teach you in JC, I guess, which is the that vertical bracket, and then you write your you know, two numbers. Basically the thing that you use for PNC as well. So for example, if you use to the power of 3, the first term is basically 3 1, like 3 3 1, then 3 2, then 3 3, kind of. So no, sorry, 3 0 3 1 3 2 3 3. So you get 1 3 3 1 if you calculate that. So how does that work? Basically that means that, for example, 3 0, it will be the factorial of 3 over the factorial of 0 and the factorial of 3. And for 3 1, you would get the factorial of 3 over the factorial of 1 times the factorial of 2, which would give you 3. Yeah, so the first one is 3 factorial over 3 factorial, which is 1. So the coefficient is 1. Then the second one, I just told you, is 3. So the coefficient is 3. So likewise, this can be used to calculate all the coefficients. And then for the powers, I think it's pretty obvious how you do it. You just keep decreasing the power of the first term and increasing the power of the second term. Right, so I hope you understood what I said. So for any n, if you have a plus b holding to the power of n, if you were to expand it, you would have to write n0 a to the power of n plus n1 a to the power of n minus 1 b plus blah 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 until bn. Yeah, I'll just write it down. I think that's easier than saying it out because it's annoying to say. Okay, but here they do not actually tell us about a plus b to the power of n. They're talking about 1 plus x to the power of n. And of course, that is a lot easier. It's a lot easier because, you don't need to think about if your n is a positive n, it is definitely easier. But here they're actually showing you the oh wait, I think I talked about the wrong thing right now. Never mind, I'll probably re-talk about it when you're doing binomial distribution. But for now, just learn this once. I'll retell the same information later on. Yeah, so that's what you would do normally, right? So when you have a power, but you don't get a positive power all the time. You sometimes get a negative power, so like 1 plus x, the whole thing to the power of -1 or to -2, or maybe something like 1 plus x to the power of half or 1/4 or something like that. And in that scenario, you can just do a binomial expansion, which I just covered. You have to do something else. So according to MF26, there's a lot of formulas in there. You just need to refer to it when you're doing the exam. You don't need to memorize the formulas unless you're extra kiasu and want to save time of looking through the MF26. I'm pretty sure even if you memorized it, you would look at it once just to make sure that you're writing it correctly. But for 1 plus x to the power of n is actually pretty simple. You first start with 1. Of course, in the binomial, you realize that, the way that it's derived, the way that it works is that you have a factorial or another bunch of factorials. And in this case, what you do instead of using factorials, you just you go to nx. So you first times it by n. And after that, you go into n times n minus 1 over 2 factorial times x squared. And then so on and so forth until you reach the last term. Actually, there's no real last term. So, yeah. Because this is meant for x, modulus x lesser than 1. Oh yeah, just remember that because it's actually quite important when you have a series that doesn't seem to end per se. So when this sequence of terms can keep going on forever if you wanted to, I suppose. And in that scenario, you would want your x to not be greater than 1 or smaller than -1, because in that scenario you would it won't work very well. Let's just say that. because you want the x to keep getting smaller and smaller as the sequence proceeds. Like you want your x to the power of r to be smaller than your x in that sense. And for that your x must be in between -1 and 1. Yeah. Okay, so because if it's for example 2, right, then your subsequent term will get bigger and bigger, and you cannot ignore the terms already. You have to actually keep doing it forever and forever, which is not fun. But if your x is really small, or like decently small, like half for example, each subsequent term can be more and more ignored in the sense, and you can just write the first 3 terms or first 4 terms in order to so-called approximate the value of 1 plus x to the power of n, where n is not necessarily a positive n, in the sense, or it's not a whole number kind of n. Okay, so let's move on. So the next one is e to the power of x. E to the power of x, well, in MF26 it says that e to the power of x is 1 plus x squared over 2 plus x squared over 3 factorial, and so on and so forth. I think this is like the easiest one to do because, you know, it's very consistent. You just have 1 x squared over 2 factorial, x cubed over 3 factorial, blah 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 blah. And in fact 1 is like x to the power of 0 over 0 factorial, which is just 1. And x is just x over 1 factorial, which will give you x. Yeah, so this is pretty straightforward and it works for all x. And then sine x will give you x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial, and so on and so forth. So yeah, there's a reason why it's written in MF26. You're not going to go around remembering this in your head. The other method that you can use is actually do the Maclaurin expansion and then find out what sine x expansion would be. And this also applies to all x. For cosine x is 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial, and so on and so forth for all x. And finally, for ln of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus blah 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 blah. Okay, cool. This is fine and all. You can easily look at this MF26. So why am I saying this again? Why do I even care? Okay, so before we move on to the stuff that I actually care about, let me tell you why all of these expansions work. If you look at the expansion right on top of the list, which is the one with fx, you see that the Maclaurin expansion is fx equals to f0 plus x times f prime 0 plus x squared over 2 factorial times x 2 0, x prime prime, I guess, and so on and so forth. So the reason why this is done in this manner is, if you first start with fx, let's say you have a curve fx, and you know, the reason why we're using 0 here is I don't know. So 0, it would be maybe like the starting point. It's the origin, of course. So you get f of 0, and then you get x times f prime 0. So say you have your point at x equals to 0, and then you have your gradient of that point at 0, I guess, and you times that by x, and then you have x squared over 2 factorial f prime prime 0. So let's say you already got the gradient and you derive it further, you add and you times it by x squared over 2 factorial, and so on and so forth. So do you think this actually, accurately approximates something? The reason, I guess it does, because first of all, the x is actually involved in the series. That makes sense, if that makes sense to you. And if you think about it, if you put a tangent at fx and you just let it extend in both directions, of course, you do realize that the gradient of f prime x, right, the gradient is f prime x. And since you do not know what is f prime x, because you don't know what is x yet, you can, and actually f prime x is not helpful, so you need to know what is the x, it's fx itself in a sense. So let's say fx, wait, what am I even saying? Okay, yeah. Uh, I don't know whether I said anything useful for the past 1 minute. Oops. Okay. Okay, so for x, so if instead of timesing it by f prime x, which wouldn't make sense because why the fx isn't obviously f x times f prime x, because that doesn't make sense. You times it by f prime 0, because if you think about it, if you use a linear approximation or some kind of, that kind of thing, you can imagine it as y, in other words fx is equal to, you know mx plus c, in which m is the gradient, and we do not know what the c is in this case, so we're going to assume that this mx is the gradient, is a line from 0 to x. Wait, no, that doesn't make sense. I have no idea what I'm doing. Yeah, like the line from 0 to x, and then you use that as a gradient. And then you do this for subsequent terms, and it becomes more and more accurate in that sense. Yeah. I hope you understood what I mean. So anyway, just ignore me because, But if you were to integrate all the terms here, um, f0 is going to be a constant. So it's going to be x times f0. And then f of f prime 0 will become something else. Actually, that's not really helpful. Let's just ignore what I said for the past 2 minutes and move on. So let's all just agree that the Maclaurin expansion works. And from there you can actually derive each of the subsequent expansions. So like for example, if you're gonna use EX, which is the easiest one, that's why I'm using it. Let's say EX, if F0 is what? 1, obviously, e to the power 0 is 1. And then F prime 0 is also gonna be 1, and to be forever 1 and forevermore. So that's why in the e to the power of x there is absolutely no e to the power of anything written there. It's all just x to the power of something over that something factorial in the sense. And likewise you can do this for any of the other terms, and you will find that this is actually just derived from the Maclaurin expansion. Okay, so after I tell you things that are super obvious, let me now go to something more useful. Okay, so you have the Maclaurin expansion right there for you, don't need to memorize it. So how do you use it? In the question they'll ask you to use it, I guess. And in order to use it, you first need to find out what is all those differentiated, terms or equations. So like for example, if you have a fx, you had to find out what is f prime x, f prime prime x, or so on and so forth. I think you'll probably be doing it until f3x or f4x. And by 3 and 4, I mean the one in bracket, not the one on its own. Because if you want to say multiple primes, but you don't want to keep saying prime, 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 you can write the number and put it in a bracket instead. That works, I guess. You can see it in the MF26 as well. The n is represented that way. So you have to keep differentiating the terms, and once you're done differentiating it, you can sub it into the Maclaurin expansion by finding f0 for all of those terms, like f0, f prime 0, f prime prime 0, and so forth, so on and so forth. And usually the question will ask you to do implicit differentiation, or you will already know that you need to do implicit differentiation, because the terms will be quite mixed up. Like there'll be y and x in the same term, or there's going to be a lot of y terms in the list, and you need to actually differentiate the y terms. And last time I told you how to do implicit differentiation, so I hope you know how to do it and you apply it properly here. Okay, so Yeah, so that's how you do Maclaurin expansion. It's actually very easy. I don't know why I'm talking about this for so long. I sound like some I feel like I'm just saying things that you already know. Yeah. Uh right. So now we can move on. Um yeah, in the syllabus it says the three ways that you can find the first few terms is either by repeatedly differentiating a term. Like for example, if it's a trigonometric term, you can just keep differentiating it. Repeated implicit differentiation, like what I just said, or you use one of these series that you can find in MF26, which I think is pretty easy to do. So I'll just talk a little bit about that and then we'll move on. Okay, so when it comes to using series, they won't just ask you to be like, oh, find the first three terms of e to the power of x or something that would be too easy, they'll ask you they'll give you instead like a product or maybe addition or something something that is a um combination of two of these series. Like for example, it could be e to the power of x plus um 1 plus n x to the power of n, or it could be even them multiplied together. So when it comes like that, you had to actually do the individual algebraic addition or multiplication for each of the terms. And usually the question will ask you to do it until x about 3 or something like that. And in that case, you have to be extra careful and make sure that if it's not just about first three terms or something, it's like each of the terms that can contribute to that power must be included. But you don't need to include terms that are definitely greater than x to the power of 3. Like for example, you have x to the power of 4, then you can just ignore it already. But if there is an x of 3, you must include it, especially if one of them has a 1 in the equation. So if there is no 1 in any of them and you have x to the power of 3, then actually you don't need to include it because you'll multiply it to be greater than x to the power of 3, like x to the power of 4 or 5 or something like that. So that's just how it's gonna be. And yeah, you just do the multiplication and so on and so forth, and just remember to write the dots at the end so that you don't lose the idea of it being a continuous, like a so-called infinite series sequence of terms. You must remember to write the dots unless you use the approximate symbol instead of an equal sign, which is the squiggly line over a straight line, that one. If you use that, then you don't need the dots. You can do that at the last step and write it in a concise and simple way. So please do simplify your terms. That's important. Okay, so let's move on. The next thing written here is range of values of x for which a standard series converges. Okay, so I read you all the series earlier. Also for ln 1 plus x must be in between -1 and 1, but it cannot be -1 itself. Yeah. So it includes 1 but not -1. And for 1 plus x to the power of n, the x cannot be 1 or -1 but must be in between them in a sense. Okay, so when you have a term, they will not give it to you as simply as like what 1 plus x, they may give you something like 1 plus x over 4 or 1 plus 2x or 1 plus I don't know, or it may not even be 1 plus x, it could be something like um 2 plus x. Okay, actually that's not very creative, but okay, still let's say it's not 1 but it's just 2. Then you might need to split it up into 1 plus x. Yeah, which would be quite annoying, so never mind. Or it could be something that's not even, but actually for 2 plus x you don't split it up into 1 plus x, you instead divide it by 2 inside the bracket. So 2 plus x is equal to 2 times 1 plus x over 2 in a sense, and that 2 must be brought out, so 2 to the power of n as well. So 2 to the power of n, and then the bracket will be 1 plus x over 2 to the power of n. Okay, so yes, I guess it's pretty simple. And of course, in the syllabus, one of the examples they gave was ln 1 plus x or 1 minus x. And in that kind of scenario where you have a slightly more complicated logarithmic term, or even a term that's not ln but instead of log 2, log 3, log 10, or something like that, you can just convert it into ln using the powers of, using the rules that you have, I guess. So for ones that are entirely in ln, I think it's pretty simple. Like what if you have a quotient, you can this minus that. If it's a multiplication, is this plus this, and so on and so forth. If it's like a power, then you bring the power in front like as a coefficient. And if it's something like log 2, log 3, there is a formula to actually convert it into ln. I think if you do not know this yet, it would be very helpful to know it. So for example, log 2 4 is equal to 2 of course. Well, it is 2. So log 2 4 is equal to ln 4 over ln 2. So that's how you can make something into a ln, and you can use that to do your series expansion without a hitch. If not, you can always do differentiation, but then you will still need to convert it to ln in the sense, so yeah, might as well just do that. Okay, so right, let's move. So for the range of x which the series converges, as I mentioned earlier, the x must become smaller and smaller as the power increases. So in that sense, you just follow the values of x that are written in the brackets in MF26, and you think about it logically, because you usually won't get x, you get something like x over 2 or something, and you just think about that instead of x. Like you replace the x in that bracket with the term that you get, and then you work it out and see what x should be. I think that's pretty straightforward. You should know how to do it. Don't get confused by this particular question, and yeah, I guess that's okay. So finally, we will go on to approximation. I guess this is the only other useful thing here. So the concept of approximation and how approximation works is that, let's say you have a gradient or a value that you want to calculate, and you do not want to, and you don't really have like a very good calculator or something that allows you to get the value. So instead, you want to approximate the value. Like for example, you have sine to the power of, now sine I don't know, 1.01 or something, some weird angle like that, and you do not want to calculate that because you don't have your calculator, and you don't want to refer to those weird tables. Actually, the table might be just as accurate as approximation, but still. So what do? Approximation, of course, it works better when the x is smaller, simply because the later terms converge faster. But in general, you can choose a number of terms to keep to, like 2 or 3 terms or even 1 term for your approximation. So for example, if you have sine 0.01, which is obviously quite small, we can approximate it to 0.01 because the other terms are quite will give you many decimal places. So you can keep any terms until x to the power of 2, and after that you can remove all the other terms. And this is what is done in small angle approximation, where the angle must be very small. It cannot be using a sine 1.01. You can use sine 0.01 instead. I guess that will actually be approximation in a sense. So for sine, it will be just x. Sine x equals to x approximately. Cosine x is equal to 1 minus x squared over 2 factorial approximately. And tangent x will be approximately equals to x. The reason why you do not see tangent x in this list is because you can just derive it from sine x over cosine x, logically speaking. And the reason why tangent x is approximated to x instead of some other terms that, given that you had to divide the sine x or cosine x, is because hmm well hmm because if you think about it, right, if you were to look at sine x 1 minus half x squared, which is actually just x squared over 2 factorial, um and you have x divided by this term, you can imagine that term to be really small. So, yeah, because the x square will be smaller than the 1, obviously, and it'll be almost like x over 1. And that's why tangent x is approximated to x, especially for a small angle, in the sense. And at the bottom it says exclude derivation of the general term of the series. As you can see, there's a reason for that. Even I stumble over figuring out how it works. But maybe I'll try to go read up more about it, and if you want a video on that, I can post one. But please tell it in the comments, otherwise I won't do that because I have my own stuff to do. Okay, so I think we are done for today. Oh my gosh, it's 30. Okay, never mind. Sorry for 30 minutes of video, 10 minutes into the video or something. Because the first 10 minutes is just me saying pointless things that are not related to this topic. But if you enjoyed this video and you found it useful and you find me saying pointless things useful, you can press the like button and subscribe. And yeah, with that, I would like to say thank you and bye.